Why was calculus invented? What is the purpose of calculus? Well, modern calculus was developed in the 17th century by Isaac Newton and Gottfried Wilhelm Leibniz. Newton and Leibniz didn't work in collaboration with each other, but they were publishing at the same time to where their contributions taken together are considered to be the development of the subject of calculus. But leading up to the time of Newton and Leibniz, what you can think about is that by the 17th century, the subjects of algebra and trigonometry were already, you could say, fully developed. I mean, like technically subjects like algebra and trigonometry that we're most familiar with today, what we learn in high school and what you would learn in a full course in college algebra or trigonometry or even like geometry, for example, and there's full playlists for these subjects on this channel. But you can imagine you've already got a large portion of these subjects developed and being applied to an appreciable extent at the time to solve real-world problems by engineers, scientists, business people, etc. Right? You could think about before the 17th century, they were using what we think about as algebra, trigonometry, and in geometry, in business, physics, engineering, science, astronomy, etc. Okay, but by the 17th century, there's still something that you're unable to do in algebra. And even you could look at this in a similar way as something you can't do in trigonometry or geometry. You don't have a way to calculate the equation of a tangent line to a curve at a point, right? So in algebra, we've got all kinds of curves that we mainly think about as being represented by equations. You've got functions, which are equations or graphs that pass the vertical line test. So there's no input that maps to two or more outputs, like shown here. So that this would be a function. And we can think about what would be the equation of the tangent line to a point on this function curve. Like, for example, this tangent line here, what would be the equation for this tangent line? But there's also equations that represent relations, not functions, like the equation of a circle, for example. Okay, so in basic algebra, we know how to work with equations of circles. You've got the center point, hk, that would be here 3 minus 5. And then you get the radius of the circle, so that would be 1, 2, 3, 4. So with the center and the radius, you just have x minus h squared plus y minus k squared is equal to r squared. And that's the equation for any of these points on the circle. You plug in any of these points into that equation, and it satisfies the equation, right? But again, this is a relation. A circle doesn't pass the vertical line test. You have single inputs mapping to more than one output, but still, even for a relation, you could ask the question, okay, what's the equation of the line that's tangent to this circle at this point on the circle, right? What's the equation of this line? Okay, and so this is what's called the tangent problem. Prior to calculus, there was no official established method for determining the equation of the tangent line to a point on a curve. Like, okay, if we've got the function y is equal to x squared, so this is a function, the function f of x is equal to x squared, a parabola. If you were asked, what is the equation of the tangent line to the curve y is equal to x squared that touches the point 3, 9 on y is equal to x squared. So at x is equal to 3, you square 3, you get 9. So 3, 9 is on y is equal to x squared. What's the equation of the line that's tangent to y equals x squared that touches the point 3, 9 or passes through the point 3, 9? Okay, well, with calculus, we know that the answer to this question is the line y is equal to 6x minus 9. But how is this determined? That's the big question. How does calculus allow us to determine this equation? Okay, well, now you might say to yourself, what's the big deal? If I really needed to get an equation like this, I could figure it out. This isn't rocket science, especially if you're already very good with algebra as it is. So you already understand lines in terms of equations and graphs of lines very well. And you understand equations of algebraic and trigonometric curves very well, right? So what's the big deal? And yes, in one sense, that's true. You would be right. Because, I mean, what you could do is this. In this case here, you could pick another point on y is equal to x squared off of the point 39. We'll call this point P, our point of interest, our point of tangency. Okay, but we'll pick another point Q over here. But Q is at some arbitrary location on y is equal to x squared. So we'll say it's at some point with x coordinate x, and therefore the y coordinate is going to be x squared because you just square the input. So Q is at x squared. Okay, and now from here we can think about a line that passes through both point P and point Q. That's going to be a unique line, right? Two distinct points constrain a unique line. So drawing that line, there we go. Okay, but now this would be we would call this a secant line, not a tangent line, because it doesn't touch the curve at a y is equal to x squared at a single point. All right, and so now with 2 points, a line that goes through 2 points, we know from algebra how to calculate the slope of this secant line, no problem. So the slope of the secant line, we'll say, is ms, is you just do y2 minus y1 over x2 minus x1. This is simple algebra. y2 minus y1 over x2 minus x1. All right, but now our intuition tells us that if we want to think about the slope of the tangent line, which we'll say is m, so this has slope m, our intuition tells us that, well, look, if we let Q get closer and closer to P, really close to P, then we're going to be getting closer and closer. The slope of the secant line is going to be getting closer and closer to the slope of the tangent line. That's very intuitive. Okay, so even prior to the 17th century, they could do arithmetic calculations by hand. Okay, so we could think about just plugging in an x value into this formula that's really close to 3. Let's say x is equal to 3.0001. And then doing that calculation, we would get the slope of the secant line is equal to 6.0001. And then maybe we would guess that if we could do a really big hypothetical calculation, really, really close to x is equal to 3, then we could round this to exactly 6, in that the slope of the tangent line to the y is equal to x squared curve at the point 39, we could say is equal to 6, exactly 6. Okay, and so then we have a slope, m is equal to 6, of a line that goes through the point 39. Well, okay, that's now to get the equation of the tangent line itself, that's simple algebra. You just use the point slope form of a line. Y minus y1 is equal to m times x minus x1 to write out the equation of the tangent line. And you'd get this. Okay, and so I wouldn't imagine, and maybe I could be wrong. I know a lot of things in life and science that we understand seem very simple in hindsight, but in reality, they aren't simple at all. But I wouldn't imagine if in the 17th century you had a mastery of the state of the art in algebra and trigonometry and geometry, and someone asked you to give them the equation of the tangent line to say the curve y is equal to x squared at some point. It's not like this would blow your mind as if you were thinking about some sort of quantum mechanical concept like we would think of today. Quantum mechanics is mind-blowing conceptually to humans today, right? Especially if the person asking you for this equation was just asking for as precise of an equation as you could get. So it didn't have to be some exact mathematically proven answer for the equation of this tangent line, just as precise of an equation as you could get. Okay, but however, what would potentially be mind-blowing at the time, and this is really where the challenge comes in, is if the person did ask you for the exact equation of the tangent line to a point on y is equal to x squared, or the exact equation of the tangent line to a point on any general curve, right? So the exact tangent line. equation? What is the exact slope of the line that is tangent to the curve y is equal to x squared at the point 39? Exact meaning that this is definitively defined and proven mathematically. Just like all concepts in math are definitively defined and proven. Okay, and so again, this is really where the challenge comes in. This is really where the brilliance of Newton and Leibniz lies in terms of inventing calculus. I'm not saying a mathematician, physicist like Newton didn't also publish more mind-blowing concepts as well outside of calculus. But in this specific case of calculus, I wouldn't imagine that this was like a parallel to Einstein with special relativity, space-time, etc. It would seem to be the case that if you had a mastery of the state-of-the-art in algebra, trigonometry, and geometry concepts in the 17th century, 16th century, etc., then the idea of coming up with just a solid estimation of the equation of a tangent line to a point wouldn't have been rocket science. Okay, the brilliance of Newton and Leibniz at the time was they had to create an entire system with theorems, proofs, etc., to where you could be presented with any function or curve from algebra, trigonometry, or wherever, and determine the exact equation of the tangent line to any point on that curve. Okay? Now, you might say to yourself, well, I'm not a mathematician. I'm an engineer or scientist or business person. Why do I care about getting the exact equation of tangent lines to curves? Okay, well, yes, once again, this is true to an extent. For non-mathematicians, it really isn't necessary to rigorously learn all calculus proofs, theorems, etc. But it's just like algebra. It's not like we as non-mathematicians learn algebra as extensively and in detail as a mathematician would. Okay, but we still learn it very well to where we can easily apply the concepts of algebra efficiently and creatively. Okay, but even more than that, what you can imagine is if there was some applied calculus scenario, some real life scenario that an engineer, scientist, business person was working on that required a high degree of precision, okay? Well, in that case, there could be an issue with an engineer or scientist in one part of the world using some approximation technique for the slope of a tangent line that was different from the approximation technique being used by an engineer in another part of the world. There needs to be some continuity between the calculations of everyone in the world. And that's where it's valuable to be able to use what's defined by the field of mathematics, or whatever field, to be the exact values of parameters. All right, and so to be able to formally answer this tangent line equation question, and really if you think about it, it's more of a slope of the tangent line question. It's more about finding the slope of the tangent line because you already have the point of interest given to you. You know what point you're interested in, the tangent line going through. What you're really trying to figure out is the slope in order to get the equation of the line, because then you'll have a point and a slope, and now you can just construct the equation easily. Okay, but to formally answer this question about the slope of a tangent line to a point, the idea of the limit was introduced. The limit is the foundational concept of all of calculus. The limit is at the foundation of the derivative, the integral, and infinite sequences in series. Okay, but now, in addition to the tangent problem, we also think about calculus solving what's called the velocity problem, which is closely related to the tangent problem. So the tangent problem was sort of purely geometrical, right? A literal line tangent to a curve in a plane. Okay, but if we had to think about a question like, what is the speed of a car when it runs a red light? So the car passes through the intersection and a picture of the license plate is taken. And at the moment in which the picture of the license plate is taken, at that instant, what is the speed at which the car is moving? Okay, well, obviously prior to calculus being invented, there were no vehicles, but they could still ask a similar type of question. What is the speed of something at an instant, at a moment in time? And once again, just like the tangent problem, prior to calculus, there was no way to really formally answer a question like this. Why not? Well, because we know a quantity like a velocity is all about changes in the corresponding parameters. Velocity is a change in position with respect to a corresponding change in time. So how could you think about a velocity at an instant then, at a moment in time? You need a change in time to calculate a velocity, right? Okay, but in reality, if you think about it, if you're asking about the instantaneous velocity of something, what you're really asking is, what is the slope of the tangent line to a given point in time on a position versus time curve of that something, right? If this is the position versus time curve for the vehicle, and at this time t is the moment in which the picture is taken of the license plate, then what you're asking is, what is the slope of the tangent line to the position versus time curve at this point in time? That's what you're asking. That's the instantaneous velocity at this time t. Okay, and so you can see that in terms of the velocity problem, we aren't concerned with the tangent line itself or the equation of the tangent line. We're just concerned with the quantity that corresponds to the equation of the tangent line. The velocity problem is really just the tangent problem viewed from another perspective is all. Okay, but now, as far as how do you solve the velocity problem, well, again, the tangent and velocity problem are really the same problem. You need to find the slope of the tangent line to a curve at a point. That's it. And again, to solve this tangent line slope problem, the concept of the limit was introduced. And with the limit, the concept of the derivative is developed, which is the main tool you use to find slopes of tangent lines to curves. You can think of the derivative as the software you interface with on your computer. You open a derivative application on your computer to find slopes of tangent lines to curves, but in the background, the code of that application that runs the software is based on limits. Okay, but now also you want to think about how the velocity problem really isn't about velocity. Velocity is just a quantity that's used as the main example, right? This is really more about the ability to calculate a change in a dependent variable with respect to an independent variable at an instant of like a single input independent variable, right? Like you could have a supply demand curve or a price quantity curve, and you want to think about what is the change in price with respect to quantity at a given value of quantity, right? So then it's the same idea. You want to know what's the slope of the tangent line to the supply demand or price quantity curve at the given quantity. You see? Okay. But now, the tangent and velocity problems weren't the only quantities that couldn't be formally calculated at the time, leading up to calculus. Prior to calculus being invented, you also have what's called the area problem. So with geometry, you could determine areas under certain curves. So the area under a straight line could be determined based on the area of a triangle. If the area under a curve corresponded to a specific type of geometric shape, in which area formulas were already proven in geometry, then that area could be determined. But in general, for any general type of curve in algebra or trigonometry, right, a logarithm, exponential, trig function, polynomial, etc., there was no official established way to find the exact area underneath a general curve like this over some interval. And again, just like with tangent lines, it's not like this concept was mind-blowing rocket science to just give a very good approximation for a certain area. But to give an exact answer to a question like this, along with an official, established, formal way of determining that answer, that is a challenge. That is potentially mind-blowing. Okay, and once again, this question is it was formally answered using the idea of the limit. And with the limit, the concept of the integral is developed, which is the main tool you use to find areas under curves in any circumstance. So for any curve on any interval of that curve. Okay? But in addition to the area problem, we can also think about what's called the distance problem. The distance problem is to the area problem what the velocity problem is to the tangent problem. So let's say you want to determine the distance something travels between time t1 and time t2, and you have the velocity versus time curve. Well, to determine this distance, s, what you need is the area under the velocity versus time curve between these two time points, t1 and t2. You need this area here. And if the velocity versus time curve isn't a straight line or making some known geometrical shape, then prior to calculus, you would have no way to really formally answer a question like this. Okay, but once again, you can see how the distance problem is really just the area problem from another perspective. Both are the same thing. If you solve the area problem, then you've automatically solved the distance problem. Okay, and then also you can notice how the distance problem, just like the velocity problem, isn't really about distance. It's really about, in general, any scenario, a relationship between any two variables, like a price versus quantity curve. It could be the case that the area under a curve, like a price versus quantity curve, has a real life meaning that you're interested in. Okay, and so that's mainly what calculus is all about. That's it. The entire subject of calculus is really all about finding slopes of tangent lines to curves, as well as finding areas under curves. Also, at the end of Calculus 2, after integrals, we talk about infinite sequences in series as well. But the large portion of all of calculus is about derivatives and integrals, which is all about finding slopes of tangent lines and areas under curves, and then specific applications of these concepts of derivatives and integrals. What do derivatives and integrals allow you to understand about algebra, physics, etc.? That's it. Okay? And then in Calculus 3, all we're doing is extending calculus past single variables. So single variables is just one input and one output. We're extending calculus to multiple variables, so multiple inputs and output, for example. Like here, we might want to find the volume under this surface, which would be done with double or triple integrals.